I am just a user of Sage, not that I have developed anything. I usually use mainly for pedagogy purpose. Okay, so sorry for inconvenience. So first of all, yeah, so this talk is going to be a very brief introduction to SageMath. First of all, I apologize to those who are already using this, and I see many people are quite expert in this. They are not only using, but they are also developers. So it's my apology to them. So let's see, what is SageMath? So how many of you have heard about it? I would think majority, right? That's why you are here. But still I see a few students who haven't even heard. But in any case, they are here, so at least I'll try to make it as simple as possible. And I'll also show some of the basic things which is quite useful. And the one thing which I would like to say, that this is very easy to use. Unlike many other software which has generally steep learning curve, this is quite easy. So that you will see that. So what is Sage? In general, SageMath. It's a free and open source mathematical software, but it's basically a computer algebra system. So when I say computer algebra system, some of the computer algebra system you must have heard: Mathematica, MATLAB, Maple, Magma, and there are several others. Most of the, all these which I mentioned, they are all proprietary software. You need to pay lots of money in order to have your single user license, whereas SageMath is free and open source. All of you understand what is free. All of us love free things, right? But it's open source. It simply means that you can also see the source code. Not only just you can see the source code, but you can also make changes and distribute. So that's the meaning of free open source packages. So SageMath is one such. So let me just briefly run through some of the things which I have noted. So as I said, it is a free and open source sophisticated computer algebra system. Computer algebra system means that it can do basically 4 things. One, it can do numerical computations. That's what you would expect. If you have any mathematical software, you should be able to do numerical computations. You can also do symbolic manipulations, which we do a lot in mathematics, right? And generally symbolic manipulation is somewhat harder for in computers. So this SageMath can do symbolic manipulations. You can also do plotting of basic 2-dimensional and 3-dimensional objects, including animations. And you can also write program. Most of the computer algebra system will have its own programming language. So not just you can use the ready-made available function, but you can create your own functions, methods. In particular, you can write program. And this is actually built on several free and open source software. So when the development of Sage started way back in 2004 by Professor William Stein, that time already many free and open source softwares were there. So he thought of not to invent the wheel again, reinvent the wheel, but then rather than he wanted to create a platform from which many of these free and open source software can be used. So that is how he initially created. So that time already many software, including R, then Maxima is also another computer algebra system, plus Singular, and many of those. You can go to this link and look at what are the softwares that is part of this. And actually it comprises of several packages, close to 300 packages that list you can see from this GitHub page. And this I already mentioned, it supports numerical computations, symbolic manipulations, graphing, and programming. The actually main aim of creating this beautiful software was to create a free and open source viable alternative to these big 4 M's like Mathematica, MATLAB, Maple, Magma. In fact, when Professor William Stein created this, he was using quite extensively Magma, and he wanted to do something which, because of his closed source, he couldn't do. So he decided to create this. If you look at his website, I think he has written why he created this software. Almost, I think, some 16-17 pages of document is there. Of course, he mentions all his experiences regarding development of software that he has done. So this first version of Sage was released in 2005, and as I said, most of the computer algebra system has its own programming language, but then SageMath native language is Python. So in case you know a little bit of Python, it will be quite easier to use. And but even if you don't know Python, still you can use it quite efficiently. So how many of you already have done some basic course in Python or basics of Python? I think again majority, right? So that's good. These days Python is becoming extremely popular. In fact, many universities, they are replacing C, C++ with Python, because it's very easy to use language and very powerful, which is extensively used in scientific community, as well as these days popular domain called data science. It's very popular there. So if you are good in Python coding, etc., you can even get a good job in industry. Right, so it is based on Python programming language. So it doesn't have its own programming language, right? It uses Python in its background. Right, and so as a result, you can just write Python programs from SageMath worksheet itself, and conversely, you can also import Sage as a library in Python. Though, I mean, I have not done that. Whenever I have to write Python programs in SageMath, I just do other way around. Yeah. So, as I said, this SageMath, the way I have been using is basically for pedagogical purpose. I use quite extensively in my teaching, basically for linear algebra, calculus, including multivariable calculus, group theory, optimization, also numerical analysis. In all these things, whatever I have been teaching, I use quite extensively. And in fact, at our university, we also have a course on software lab where we teach SageMath. So I find it is very nice teaching tool, but you can also use it in research, and many people are using it quite extensively. If you go to the SageMath website, sagemath.org, you'll see a page on a list of publications, and you will find that there are several papers which are listed there, and of course there will be many more which are not even listed, but they have used SageMath. So, and one good thing about SageMath, I'm sure most of you must be using LaTeX, a typesetting tool, mathematical typesetting tool. So it has very nice interface with LaTeX. So two things. One, if you create any object in SageMath, you can create a LaTeX code and you can put it in the LaTeX document. That is one part. So that is, we as a teacher, it's quite useful. Many times, especially when we want to write our lecture notes and which has a lot of computations, then I do the computation in SageMath and simply generate LaTeX code and put it in the notes. And other way around also is true. There is a package called SageTech. Using that SageTech, you can even call SageMath from LaTeX interface itself. So that is also very, very nice. I'm not sure, possibly few of you might have already used SageTech, but that feature is also there. And of course, it can be used in all the platforms like Linux, Windows, Mac. What I'm using is Windows system. So in Windows, I think nowadays you can use it, you can install Sage through what they call WSL, I think Windows Linux system. Earlier they had the executable file available, but I think latest release, which is 9.6, I didn't find that. Maybe after some time they may release, possibly those who are part of the development team can guide us. I think there is a session on installation of SageMath, right? So there possibly you will learn a little more about that. And you can also use it online. You need not install in your laptop. The two ways you can use, one is from SageMath, there is a Sage cell which allows you a single cell, and it is you can write all the codes and run this. Not just that, you can put it in your website. You can insert this Sage cell in your website, and then you can allow user to do the computation. But you can also use from CoCalc. You'll have to create your login ID, and then you can use. Of course, CoCalc is also somewhat you can use it for free, but if you want to use it and you want to make use of a lot of memory and do heavy computations, also want to collaborate with others, you may need to pay a little, I think, money. But just for simple use, an individual use, it's free, and you can use. Right, so I think I've already said why to use SageMath, but as I said, it's free and has amazing capability. It's as good as all these software which I mentioned. Only difference possibly is that all these proprietary softwares like Mathematica, MATLAB, Maple, etc., they are there in existence for quite some time. They have developed quite a bit, but in Sage the capability is there. You may not find everything in the form of ready-made use, but you can write your own program. You can create a program and make use of it. So you can use in most of the topics that you generally do in undergraduate, postgraduate, including some specialized topic like manifolds and things like that. So it has several packages. For example, if you are using graph theory, there is a graph package and you can do most of the graph theory concept. Similarly, combinatorics is there, and you also have it's quite good for number theory and other things, etc. What I find is especially very, very interesting and much better than any other software is the capability in linear algebra. I use quite extensively. So as I said, it's free. It's being Python based. It is quite easy to learn and use, and it's a very nice pedagogical tool. That is how I look at mainly. And of course, it can be used even if you are doing research. So as I said, it can do symbolic manipulations, and I'll show you some of the codes. Right, so let's get started. What you see here is I'm actually using Jupyter Lab. So Sage, earlier it used to have its own kind of interface, but nowadays by default it uses Jupyter Notebook, which is Python, default Python notebook for this, and also the next version of Jupyter is Jupyter Lab, which has little more feature which I like, so that's why I'm using that. So once you install this SageMath in your system, you can use it in console, or you can use it as a notebook through Jupyter Notebook. Unlike MATLAB and Mathematica, etc., it doesn't have separate kind of GUI. Right, so that's also a good thing in case you are already using Python, then I'm sure you will be comfortable using Jupyter, and then it is very, very natural extension to use SageMath in case you have basic knowledge of Python. But in order to get started with SageMath, you don't need knowledge of Python actually. Right, so this is the input-output cell. So let us just look at if you simply want to, for example, add numbers. I just put some number here, put add plus here in between, and just shift and enter or control enter, it will give you the output. So that's adding to numbers. Similarly, if you put star, it will multiply numbers. If I want to find square root of some number, I'll simply say sqrt. So by the way, Sage is case sensitive, so the small letters and capital letters are different. So if I say, for example, square root of 5, it will just return the same thing, sqrt5. So it depends what you are looking for. So if I want the numerical value, there are multiple ways of doing. Instead of 5, I can say 5.0, and then it will give me the numerical value with a certain number of decimal places. Or I can say that sqrt and then 5, and then I can say dot n and then empty parenthesis. Then it will give you numerical. Just one second. My computer for some reason has become slow in last couple of days. I don't know what has happened. Okay, so but yeah, so this is how you can get. In fact, you can ask it to show this in a symbolic form. If I say show a square root of SQRT5, you will see the symbol which we are used to, right? So actually, for example, if I say LaTeX SQRT, or okay, I'll come to this is too simple to demonstrate. Okay, so or let us say I just use some number. Maybe let me say define a number and put it in a variable a, some number. Let me just this equal to this. Let me end by 7. So this is my, let us say, number. A is equal to this number. Okay. Now let us say we want to know what can you do with this number. First of all, of course, the units place is 7, so it's a odd number. But what is that you would like to know about this number? Can somebody tell me?
Is it prime?
Oh, you want to know whether it is prime number, right? What else? If it is a prime, fine. If it is not a prime, then we'd like to know what are its factors. If it is not a prime, maybe we want to know, suppose I am looking for some prime close to this number, what is the next number to this which is going to be prime, or what is number just close to this and less than this which is a prime. All these things we can do, and you don't have to actually remember anything. So now here this A is an object. Now I'll say A dot, and then I will press tab. A dot, and then press tab. You can see here you get a list of methods that you can apply to this object. So this is a very nice feature. This Python, as you know, it is an object-oriented programming language. So here A is an object, and whatever methods you can apply to A, that you can get it by just dot and then tab. And you see that you can go through this list. For example, there is something called divisors, and Professor Amritanshu wanted whether it is a prime or not. So there is a function called is underscore prime, and then you have to put empty parenthesis, right? Now, so this is actually basic philosophy in Sage. If some keyword consists of more than 2 words, right? Some method or function consists of more than 2 words, they will join this using underscore. For example, in Mathematica, it will be, they will put capital IS and then capital P, right? So that, I mean, different software, they follow certain patterns so that it is easier for you to guess. So if I say this, it is prime or not, immediately I get the answer, this is not a prime. So if it is not a prime, maybe I can find out factors. So A dot, and then I can press tab and then look at, right? So since I know the function, I will just run this A dot factor. So these are the only 2 factors. You can ask for prime factors also, and you can say, if I say A dot previous prime, it will give me the prime which is just before this. So I think last number was 567, this number is 493. Similarly, I can ask for, now you can even guess what should be a function or method for next prime. What should it be? What should it be? It should be A dot next underscore prime, right? So previous is previous underscore prime, next will be next underscore prime. So I can just say X A dot next. So you can also actually type few characters and then press tab. Then it will show you list of functions that can begin with those characters which you have typed. Okay, so you can say next prime, and that's it, right? So, and in fact, it is very, this SageMath is very good as far as number theory concept is concerned. So most of the thing that you have learned in number theory you can very easily explore in this. Not just that, actually you can deal with numbers over finite fields. So for example, this k dot a, this gf, and then if I say 5 to the power 45, this means, what does it mean? This is a finite field in A of size 5 to the power 45, right? So you can deal with concepts over finite field. We'll look at some more also, right? So for example, I can find out what is multiplicative order of this number, A dot multiplicative order. So this is quite huge, right? Right? Similarly, I can check whether this is a square. So again, the function you can see that is underscore prime. So whenever you want to check something, the function will start with is underscore. So if I want to check whether some matrix is symmetric, it should be is underscore symmetric, right? Yeah, so this is, it says it is true, it is a square. So you can even find out square root. Let us say put it in B. So this is the square root of this, right? And if I want to find the square of this, you will get A, right? So this is very simple symbolic manipulation done over finite field, but you can do many more things. For example, if you have two numbers, let us say if I give you two numbers, A and B, 282 and 384, right? So this means that A comma B equal to 282 comma 384. This what it will do? It will assign 282 to variable A and 384 to a variable B. That's how you can write. You can write it in different line also. In many packages they will not accept like this, so you have to say A equal to this, then followed by B equal to this, or in some other form. So if I have two numbers, what is that you would like to find out? If I have two integers, GCD, right, or LCM. So all these things are inbuilt. And actually whatever concept, so if I have GCD, the function should be GCD, right? Factor, it's factor. If it is factorial, factorial, or something very close to that. So it is not difficult to kind of guess, right? And once you have guessed, you may or may not, I mean initially you may not know how to use it, but then you can take help, right? So for example, if I say GCD of A comma B, it is 6, right? Not just that, you can even find out. Let us say, all of you must have studied Bezoar's identity, right? So if D is GCD of A and B, then what do we know? There exist integers x and y such that x times A plus y times B is equal to D, right? So in fact, you also do how to construct that, so you can write program for that. But here there is already inbuilt function called xgcd, and then when I say A comma B, it will return three things. So first one is it returns three tuple. So first is your D, second one is X, third one is Y. Okay, so if I want to store these three things output, I can simply say A comma, let me put here D comma, let us say X comma Y is equal to D. This would mean that D will be 6, and the second output will be stored in X, third will be stored in Y. If you want, I can say, I can print X comma Y comma, so D comma X comma Y. That's what you can see, right? So now let us verify. If I want to say is D equal to, or let me put it this way, X times A plus Y times B, is it equal to D? So we are checking here whether D is equal to this. So when in computer, if you write A equal to X, it means that X is stored in a variable Y. So if you want to check whether these two things are equal, you have to use logical equality, which is double equal to in this case. Now we know that the answer should be true. That's correct, right? So in fact, you can also do the similar thing for polynomials. So let me just show you. For example, you create a polynomial QQX, polynomial ring over in variable x, and I've defined two polynomials, let us say f and g, right? F is x square plus 2 times x cube, g is x square plus 2 times x minus 3, and then again you can find out over QQ dot x GCD of univariate polynomial f and g. This gives you, so I'm not going through each and every code, but I'm just trying to demonstrate. So you can see here GCD is x square plus 2, and instead of x and y, since already it is x here, it is giving me u and v. If I want to verify whether u times f plus v times g is equal to g, the answer is true. So not only you can find GCD of integers, but you can also find GCD of polynomials. Okay, so and including this Bezo's identity for this, right? So you can look at other concepts like Euler-Phi function, or even you want to do Chinese remainder theorem, and all these things you can explore, right? So next, let me say, if I want to define a function, let us function of one variable. So I have just taken this function sine of x square plus x into e to the power 2 minus x square plus x square minus 3x plus 1, some arbitrary function I have taken. Okay, right? So by default in Sage, x is taken as a variable. Any other thing, if you want to use as a variable, you have to declare. I'll show you how to do that, but by default x is a variable. Okay, so let us define this f of x. This is a function, right? If I ask it to print in pretty print format, I can simply say show f of x, then this is a function, right? This is how, if you write in LaTeX, this is how the output will look like. And if you want to generate the LaTeX code of this, I can simply say LaTeX of f of x. LaTeX of f of x. You can see here now, this is the LaTeX code. And you can write LaTeX codes in this notebook itself, right? So let me just copy this fellow. I have copied this output, and I'll go to the top. I'll insert a cell, and then instead of code, I will convert this into what they call markdown, and I will write a LaTeX code here. So each of these cell you can convert into code cell or markdown cell. So now let me say, let us explore the function $, and whatever I copied I have just pasted here, and then I will say enter. Now you can see here, right? I have written LaTeX codes here, including the text and the formulae. So I can make this notebook my lecture note, interactive lecture note. I can have a statement of a theorem, I can write even proof, I can do the computations, I can do plotting, animation, all these things can be done here itself, right? So that's the beauty of this. That's why I like this. Is a very nice pedagogical tool for we teachers, right? Okay, so let's go ahead. Now, since we have defined this function, okay, now let us look at what you want to do with this function. Yeah, tell me what you want to do with this function. So I have given you a tool, a toy. If you are a kid, it is a toy, you want to play with it, right? So what is that you want to do with this function? You want to know more about this function, right? What do you want to do? Differentiate.
Some extreme point.
Find some extreme points. Yes? What else? So you have to come up with the questions. In fact, if you are learning these kind of tools, you have to ask questions. Not that in class we don't ask. Wherever you want to learn something, you have to keep on asking questions. You may or may not be able to answer, right? Since already you have done a lot of mathematics, yes, so differentiation, finding extreme points. What else? Want to plot curve, plot graph of this function. So let us first plot graph of this function, right? Once we know the graph of a function, many things becomes quite easy, right? So let us plot. So again, what is the tool we'll use? We can simply say F dot and press tab, right? You can see here there are tons of methods that you can apply. So one thing, you don't need to actually remember all these codes. Dot, tab will tell you most of the things, right? So for example, if I say F dot and then there is something called plot. So plot. Now as a beginner, you don't know how to use this function, right? So what will you do? You would like to know more about this plot function. So you can simply say question mark, F dot plot question mark. Either one question mark or two question marks. Let us use one question mark. And now let me press enter. It's sticking, yeah. So it has given you a help document, right? Plots a symbolic expression, all the arguments are passed onto the standard plot commands, etc. And it gives you several examples. You can copy any of these examples in the notebook, right? Okay, so let's do that. Okay, so the easiest thing is you can simply say F dot plot and put empty parentheses. That's the easiest thing to do. Whenever you see when you apply dot tab, you can try this, there is something default. So let's, yeah, it has plotted. Okay, this is the graph. So what do you see? Let me show you down. What do you see? What can you conclude? It has plotted, of course the color is blue, that is one, right? But if you look at the domain in which it has plotted in -1 to 1, right? It has plotted in -1 to 1. So if you say F dot plot, and will by default it will plot in the domain -1 to 1. If I want to give the domain, instead of -1 to 1, let me say -2 to 4. And then I can also put, let us say color, in some other color, let us say red. So you can, the figure size is slightly more, so let me reduce the figure size. There is an option called fig size is equal to, let me say 5. Now it should be smaller. So these are the, so in this domain, this is how the function looks like. Now you can very easily guess, right? Some local maximum, local minimum, right? And then we can compute. So that plotting is done, and you can do all the decorations that you want. Change the color, change the design, put some annotations, all these things are possible. Okay? Right, so what else do you want to do? Somebody said you want to find derivative. So again you can use F dot tab and then see in the list whether there are something which is close to differentiation. And so if I say F dot DIFF, right? There is a DIFF, there is also differentiate. Let us use just F dot DIFF. This is the first derivative, right? This is the first derivative. Now, instead of first derivative, and it has given as a function of x. This arrow means this is the right hand side, this is a function of x, right? That's how we write function, isn't it? So exactly the same philosophy here. So if I want to find, let us say, fourth derivative, or let us say third derivative, I can simply say F dot DIFF and 3 in the bracket, it will give me third derivative. right? And you can even plot graph of both this. If let me store this in maybe F3, and I can say f dot plot again -2 to 4, and color equal to, let us say, red, and the other one I'll have to just put plus. So I will say f3 dot plot, and then I think I did not close this quotation, right? f3 dot plot, again -2 to 3, -2 to 4, and then let us say color is equal to blue. Both the graphs will appear. Oh, I did not execute this. I renamed, but I did not execute. That's why it says that name f3 is not defined. Okay. Now both these graphs are, of course, this f3 it varies. It becomes quite large in this domain. That is why you see. So I can let us just use between -1 and 1. Then you will see both the graphs. Yeah, still, right? Okay, fine. So then I think some of you wanted the critical points, right? Local maximum, local minimum. So if you look at the graph, let's look at this graph, and if I want to find, let us say, this point, this is a local maximum, right? So again, you can use f dot, and there is a function called find local maximum, and you need to mention the domain, right? So in this case, I can say between 0 and, let us say, 2. So 0 and 2. Okay, so of course it finds numerically, right? It finds the numerical value, so the minimum, the local maximum occurs at 0.6728. Of course, it will use some numerical algorithm, and the minimum value is this. Okay. Similarly, you could have found the point of intersection with x-axis, that is zeros. So you can simply say find zeros. F dot find underscore root. Find root, and again you need to mention the domain in which it has a root. So for example, it has a root between 1 and 2. So if I say 1, 2, it will give me the answer, right? So of course, when I am teaching, I may not just I may also ask my student to write their own code, whatever methods they have learned to find zeros and local maxima, local minima. In case they have learned that algorithm, I will make sure that they also write their own function. It may not be as exhaustive as the one which is inbuilt, but they will, I mean, at least it will make sure that they have learned the concept well, right? So similarly, so other things are also there. So for example, if I can find Taylor's expansion of f dot Taylor, right? So I have just said TA and press tab, and then, and what do I do if I want to take help? Question mark, right? I use single question mark. Now let me use double question mark, and then see what it gives. Again the same thing, and it also showing me a little bit of codes, how the program has been written. So that is why I call this as a open source, right? So it also tells me, it also gives you the path in which this program is written, for example here, right? So you can go back and access that particular Python program, you can make changes, and all these things you can do, right? So again it gives you this, you can see here Taylor, the function is cos minus sec, and about x with respect to x at the point 0, and degree is 5, right? So, and the same function Taylor will find Taylor's expansion of two variable function also. So usually it is not that if I have to find Taylor's expansion of two variable, that function is different than one for one variable. So that also is quite nice. You don't have to remember multiple functions for the similar concept. So let me just do that. F dot Taylor with respect to x, maybe at 1 or let us say 0, and of degree let us say 8. Okay, it will take little time. Yeah, it has given. Okay, so all these things you can do very nicely. First variable calculus, you can do the integral and all these things. Okay, right. Similarly, if you want to let us say solve some equations, what should be the guess? What should be the function? We should try solve, right? So I can simply say solve and then ask for question mark, or you can even type help and then solve. This also you can do. So again you can see here, it gives you description of this, right, and lots of examples. So this solve function actually it can solve one equation in one variable. It can solve system of linear equations. It can also solve inequalities, right? So same solve, depending upon what is the parameter you give, it knows what to do, right? So for example, if I just look at this function, I'll just copy paste over there. It's quite long help document. Yeah, if I say solve this, so it simply says solve this x cube equal to y and y square equal to x. So it's a system of non-linear equations with respect to x and y, and store this in SOLS, right? So if I say what is SOLS, then it will, what at 7? Minus 11 is not. Okay, I think, yeah, I have already defined x as something, so that's why it gives you the error. So let me reset all these things. Okay, so I can say reset. So now whatever variables that I have defined, everything will be forgotten, right? And now I can, why? Oh, I have not declared the variable now. Okay, very good. So here you see that earlier I used x, by default it understood as a variable. Here y is, it says the name y is not defined, so I need to declare y as a variable. So I can say var and then I can say y inside single quote or double quote, both are same here. Now it gives me the solution, right? So this is complex, right? So you can extract this and make use of these solutions, etc. All these things you can do. Similarly, if you have to deal with function of two variables, so how do I define? Again, first let us declare x and y as variable. You don't need to keep on declaring again and again, but even I mean I have done that, but right? And then f of xy is equal to x square minus y square into e to the power minus x square minus y square. A fairly complicated function if you have learned multivariable calculus. So if I have this function, then of course again you can ask for what is LaTeX code of this. So if I say f of xy, it will give me the LaTeX code, right? And so let us see what you want to do with this function. All the standard calculus that you can do. You can first plot graph. So I can say plot 3D this time, plot 3D, and then you need to mention the fxy and the domain for x, that is let us say -2 to 2, and for y again -2 to 2, and you can mention the color and other things, etc. also, but let's just use this. So this is the function, this is the graph. Quite nice, right? You can export it and save it as a image in PDF format. All these things you can do, right? And the other concepts that you would like to do, maybe just So again you can say f dot tab, and it will give you the list of methods that you can apply to this function, right? So same as I said, f dot Taylor, you can use it for one variable function, you can also use it over multi-variable function. Same should be true for diff, right? So if I say f dot diff, now this is a function of two variables, so that means you can find partial derivatives. So if I say x here, it will give me first order partial derivative of f with respect to x. Instead of x, if I say y, it will give me first order partial derivative with respect to y. And if I say f dot diff, let us say x comma y, it will give me, it will differentiate first with respect to x, then with respect to y. So mixed second order partial derivative. And all the other concepts you can also look at. For example, you can say f dot, let us say gradient. You can find gradient of f, you can find Hessian of f, all these things you can do. F dot Hessian, let us say xy, yeah. And if I want to evaluate, let us say x equal to 1, y equal to -1, that's the Hessian, right? So, and if you just equate partial derivative equal to 0 and then try to solve the system of equations, it will give you critical points. Using solve command, you can find the critical points, and then check whether the Hessian is positive definite at those critical points or negative definite or indefinite. It will you can do local maxima, local minima for this also. You can also integrate. The function is integrate. Okay. Let me briefly tell you, it's already almost 1 hour, right? So 10:30 I'll have to wind up. Yeah. Right. So you can define vectors, matrices, and do all the standard calculations. So for example, let's say I want to define a vector. I can simply say v dot vector equals you can write your own program also. You can write your own function, right? Similarly, you can define matrices. So I have just predefined this matrix. There is something wrong. Okay, some entry I think I have made. Okay, anyway, let us just take some matrix. A is equal to, or I can, let me see if I reset. There is some comma missing somewhere? Correct. Yeah, I just, okay, fine, thank you. Right, so this is a matrix. Now, anything that you want to know about this matrix, it's there in on your fingertip, right? What I need to do? What do I need to do if I want to know about this matrix? I want to do some computation about this matrix. Dot tab, right? So I will simply say a dot and press tab, right? You can do row operations, you can find adjoint, you can find adjugate, you can find augmented matrix, characteristic polynomial, eigenvalues, eigenvector, singular value decomposition, row space, column space, everything that you learn in standard linear algebra course will be there, right? The QR factorization, LU decomposition, all these things, including Jordan canonical form. So if I say Jordan form, That should also work. Let us see. Yeah, it has given. Right? Of course, you have to check whether what you are getting is correct or not. Since computer is giving, it must be correct, right? You should not believe that, right? You should not believe, right? Make sure that what you are getting makes sense. Okay, so it can find Jordan canonical form, right? You can find row space, column space, all these things you can do. And you can define groups, and so it is symmetric group is 6, and you can do all the standard group theory computations. You can generate random elements, find order of an element, generate a subgroups, find all subgroups, of course up to certain order, right? Find all normal subgroups, find conjugacy classes, silo subgroups, all these things are inbuilt. In fact, the book which is mentioned already has it, since I'm running out of time, including, let us say, if you want to do some visualization with group lattice, you can do, right? Or even if we want to do, let us say, combine Python and SageMath, that also is quite easy. For example, the particular one, I'm using some Python libraries like matplotlib, pylab, etc. in NumPy, and I'm importing an image in this, and then segregating the red and blue and green channels, and then using matrix plot from SageMath to plot each of these channel, also including the image. Then I can find singular value decomposition of this, and then again I can take first few components of that, and then they see how this image compression can be done using singular value decomposition. So this is actually combining Python code with SageMath, right? So I didn't have time to explain, but in any case, yeah. And you can also do some interactive plotting. You can do some interactive plotting. Unfortunately, there is some issue with interactive plot from Jupyter Lab. If you want to do it in Jupyter, it will work. So you can do, there is a function called interact, using which you can do interactive plotting. You can change whatever variable you want. All these things will give you, right? And yeah, so let me just end with giving you some references. So best reference I find is you can go to SageMath document itself. You have lots of documentations. There is one book which is also there on the website itself, Computational Mathematics with SageMath by Paul Zipperman. That is very nice book. You can also look at free and online book by Robert Beezer. In fact, many of this linear algebra concept, I learned it from this book. And you can also find a set of 12 lectures which I gave during, as soon as the lockdown started, I thought what to do. So I gave some set of 12 lectures, which is there on my website. You can look at it. It covers basic calculus, linear algebra, little bit of differential equation, and I also recently gave course of lecture on computational mathematics with SageMath in NPTEL. So that course is also available. That covers starting from Python, 2 weeks of Python programming, followed by introduction to SageMath, then basic calculus, followed by linear algebra, and a little bit of numerical methods. It also covers linear programming. So that has a lot of material actually. So yeah, so you can look at this, and this is the last book that I wrote that you can look at, but there are many other books also. So thank you very much. If you have any questions, if the time permits, I can answer. It's already late by 3 minutes.
Yeah, so we thank you, Dr. Ajit Kumar, for this introduction to Sage.
Thank you very much.
Dr. Ajit Kumar is here, so we can